Hello my dear students, welcome to my channel Fluid Mechanics lecture series. I am your Sumam. We are continuing with the fluid statics. Fluid statics means we are going to study the behavior of the fluid under rest. So in static condition there are two forces to be considered. One is body force and other is surface force. Today we are going to consider the variation of pressure vertically in a static mass of fluid under gravity. So let us go and see this on illustration. Consider a container filled with liquid of constant density ρ. Figure shows a fluid element of constant cross-sectional area. The top surface is at a distance of Z2 from the free surface, whereas bottom face is at a distance of Z1 from the free surface. P2, that is the pressure acting on the top face, whereas P1 is the pressure that is acting on the bottom face. Now we are going to consider the equilibrium of this fluid element in the static mass of fluid. Two conditions are to be satisfied. To keep this fluid element in equilibrium, algebraic sum of the forces that is acting in x direction equal to 0 and algebraic sum of the forces in y direction equal to 0. The vertical forces are pressure forces and the weight of the element that is acting in the downward direction. So force due to P1 equal to P1 into the area here. So force due to P1 on area A acting up equal to P1 into A. Similarly, the force due to P2 that is equal to P2 into A that is acting in the downward direction. Now the weight of the fluid element W that is acting down. So weight equal to specific weight into volume of this fluid element. So it can be calculated as, so force due to weight of the fluid element equal to mg equal to rho g means specific weight into volume of the fluid element. So volume of the fluid element equal to A into Z2 minus Z1. If you are considering the equilibrium of the fluid element, that is sigma Fi equal to 0. So here the forces P1 into A that is acting upward, whereas P2 into A that is acting downward, along with weight of the fluid element that is acting downward. So if you are considering sigma Fi equal to 0, then P1 into A minus P2 into A minus rho g into A into Z2 minus Z1 equal to 0. So P2 into A and this rho g A into Z2 minus Z1 both are in the downward direction, whereas P1 into A that is acting upward. So if you are eliminating the common factor A that is common, then equation is P2 minus P1 equal to minus rho g into Z2 minus Z1. So what is the significance? That is P2 minus P1 equal to minus rho g into Z2 minus Z1. That means when we are moving up, the pressure that is getting reduced. So in any fluid under gravitational attraction, pressure decreases with increase of height. So if you are moving from Z1 to Z2, then pressure that gets reduced. To illustrate this, we can consider an example. A diver descends from the surface of the sea to a depth of 25 meters. What would be the pressure under which the diver would be working above that at the surface, assuming that density of seawater is 1025 kg per meter cube. Density of the seawater is given and we have to get the value of P2 minus P1. So let us consider surface of the sea is the reference level where Z1 equal to 0. Now Z2 that is below the surface of the sea, so we can consider Z2 equal to minus 25 meter. And rho is given as 1025 kg per meter cube, g equal to 9.81 meter per second square. So if you are substituting here, you will get P2 minus P1 equal to 251.4 into 10 raised to 3 pascals. You can work out this problem by your own. Let me explain the variation of pressure due to gravity from point to point in static mass of fluid. So consider three-dimensional coordinate system. So this is a rectangular fluid element within the static mass of fluid. dx, dy and dz are the dimensions of this fluid element in x, y and z direction. P is the intensity of pressure at the center. Since dx, dy, dz are small, pressure variation can be assumed to be linear within the distance dx. That is, dp by dx, dp by dy and dp by dz are constant within a distance of dx, dy and dz. Now consider x direction. In x direction, pressure gradient is indicated by dp by dx. So the pressure on the face dA, A dash, D dash can be expressed as P minus dP by dx into dx by 2. Because this face is at a distance of dx by 2 from the center, so the intensity of the pressure is equal to P minus dP by dx into dx by 2. Similarly, if you are considering the intensity of pressure on the face C, B, B dash, C dash, which is at the right side of the point at a distance of dx by 2 from the center, so the pressure at C, B, B dash, C dash is P plus dP by dx into dx by 2. So the corresponding pressure force on the face dA, A dash, D dash is P minus dP by dx into dx by 2 into dy dz. So dy into dz is the area of the face dA, A dash, D dash. Similarly, the pressure force acting on the face C, B, B dash, C dash equal to the pressure multiplied with the area dy dz. So if you are considering the algebraic sum of the forces in x direction, then we have to consider the forces which is acting on the face D, A dash, D dash and C, B, B dash, C dash. So if you are considering the algebraic sum of the forces in x direction, that means sigma fx equal to 0, or we have to add these two forces because these are the two forces in x directions, but they are in opposite direction. So that means sigma fx equal to 0 means P minus dP by dx into dx by 2 into dy dz minus P plus dP by dx into dx by 2 into dy dz. So that is equal to 0. Now consider y direction. In y direction, dP by dy, that is the pressure gradient, intensity of the pressure that is acting in the y direction on the faces D, C, C dash, D dash and A, B, B dash and A dash. So the pressure that is acting on these faces P minus dP by dy into dy by 2, and the pressure that is acting on A, B, B dash, A dash is P plus dP by dy into dy by 2. So if you are considering z direction, the pressure gradient is indicated by dP by dz, pressure acting in z direction on the faces A dash, B dash, C dash, D dash and A, B, C, D. So the corresponding pressure is P minus dP by dz into dz by 2 and P plus dP by dz into dz by 2. If we are considering the equilibrium of this fluid element, then we have to consider sigma fx equal to 0, sigma fi equal to 0 and sigma fz equal to 0. So let us go and see this on illustration. Now let us consider the force which is acting on the fluid element in x direction. So we have learned previously that sigma fx equal to 0 means this force minus of this force. If you are simplifying this expression, you will get as minus dP by dx into dx, dy, dz equal to 0. You can verify by your own. Similarly, we can consider sigma fi equal to 0. So sigma fi equal to 0 means y is in this direction. The force which is acting on D, C, C dash, D dash. Similarly, the force which is acting on A, B, B dash into A dash. So if you are expressing the equation, we will get in y direction P minus dP by dy into dy by 2. That is the intensity of the pressure and it is acting on the face dx into dz on this face. So opposite to that, pressure force is acting P plus dP by dy into dy by 2 into dx dz. Again we are simplifying, you will get as minus dP by dy into dx dy dz equals 0, or by considering sigma fx equal to 0, you will get dP by dx equal to 0. That means there is no variation of pressure in x direction. Similarly, considering sigma fi equal to 0, you will get as minus dP by dy equal to 0 or dP by dy equal to 0. That means pressure is not varying along x direction or in y direction in static mass of fluid. Now consider z direction, that is sigma Fz equal to 0. So in z direction, in addition to pressure forces, weight of the fluid element that is acting in the downward direction. So weight of the fluid element equal to rho g, that is specific weight, multiplied with the volume of this element, that is dx into dy into dz. Okay, so if we are considering sigma Fz equal to 0, we are having the pressure forces which are acting in the opposite direction. So that means P minus dP by dz into dz by 2 into z is this direction. So we are having the area dx into dy. So P minus dP by dz into dz by 2 into dx dy minus P plus dP by dz into dz by 2 into dx dy. Now weight of the fluid element that is acting down, that is into dx into dy into dz into rho g. Dx dy dz is the volume of the fluid element into rho g. So that is acting downward, that is a minus sign. So that is equal to 0. So if you are simplifying this expression, you will get as dx dy dz is common. So final expression is minus dp by dz minus rho g equal to 0, or we can write as dp by dz equal to minus rho g, or p equal to minus integral of rho g into dz. So our expression is dp by dz equal to minus rho g, or we can extend this expression as p equal to minus integral of rho g into dz, or it is equal to minus rho g z plus constant. So how will you obtain the value of constant? So for which we have to consider a container filled with liquid. So this liquid is having the constant density rho. So the pressure at the free surface is atmosphere pressure. Now consider a point x at a distance of h from the free surface. If you are considering this surface as datum, then the position of x is equal to minus h, because this is the reference level. In a fluid of constant density rho, the pressure P at any depth z measured downward from the free surface. So z here we can consider it as minus h. So if you are substituting here, you will obtain as P equal to minus rho g into dz. For the z value you are substituting as minus h. So your expression is rho gh plus a constant. So here when z equal to 0, so pressure here is P atmosphere. So at z equal to 0 means h equal to 0 means pressure equal to P atmosphere, or this constant value that is equal to P atmosphere. So if you are substituting this condition here, then P equal to rho gh plus P atmosphere. Or if you are considering P atmosphere as datum, then we can write P equal to rho gh, or P equal to h rho g, or P equal to gamma h. So gamma, which indicates the specific weight of the fluid. So this is called hydrostatic law. So hydrostatic law states that the rate of increase of pressure with the distance in the vertically downward direction at any point in a fluid medium at rest is equal to the specific weight of the fluid at that point. That means pressure at any point in a static mass of fluid depends upon its position with respect to the free surface and the specific weight of the corresponding liquid. Or we can write P equal to rho gh or P equal to gamma h. Remember, this is valid for incompressible fluid where density is constant. So in compressible fluid, density is varying with respect to pressure. So we can modify this equation as rho is varying with respect to pressure. So two levels are we are considering. In the case of compressible fluid, density is different. So we are integrating this expression between the limits P1 and P2. So that is in the case of compressible fluid where density is getting affected by the change in pressure. Now let me explain what is hydrostatic paradox. So before going to the discussion of hydrostatic paradox, let us start from the definition of hydrostatic law. Hydrostatic law states that pressure at any point in static mass of fluid depends upon its position with respect to the free surface and the mass density rho. It is not affected by the weight of the fluid present. So P equal to rho gh, that is called hydrostatic law. So consider a container which is filled with liquid up to the height h. So intensity of the pressure P, that is equal to rho g into h. Now let us calculate pressure force that is acting at the bottom of the container. Pressure force equal to P into the bottom area. So P equal to pressure into area, or pressure equal to rho gh into A. So rho g indicates the specific weight of the liquid. H into A represents the volume of the liquid in the container. That means A is the cross-section area and H is the height of the container. So the container is completely filled with liquid. So A into H represents the volume of the liquid in the container, or rho g into A into H represents the weight of the liquid in the container. That means the pressure force that is acting at the bottom of the container equal to weight of the liquid in the container. So weight is acting downward, whereas pressure force that is acting upward. So to conclude, pressure force acting at the bottom of the container, that is equal to weight of the liquid in the container. Now let me explain hydrostatic paradox by an illustration. So consider 4 containers of different shapes. So all these 4 containers have same bottom area, and all these containers are filled with liquid up to the height h. So based on hydrostatic law, the intensity of the pressure P, that is equal to rho gh, is same for all containers. So pressure force that is acting at the bottom of the container can be calculated as P equal to intensity of the pressure into area, or pressure force equal to rho g h into A. We learned previously that pressure force that is acting at the bottom of the container equal to weight of the liquid. So if you are comparing the weight of the liquid in other containers to the pressure force that is acting at the bottom, we can see that for the second container, weight of the liquid is less than the pressure force that is acting at the bottom. For the third container, weight is more than the pressure force that is acting at the bottom of the container, whereas for the fourth container, weight is less than the total pressure force that is acting at the bottom of the container. Pressure force at the bottom is to be balanced by the vertical downward forces. So there should be an equilibrium between the vertical forces. So here the vertical forces are weight of the liquid that is acting downward, whereas pressure force that is acting upward. But they are not matching. So the apparent contradiction in the hydrostatic force on the container base and the weight of the liquid inside the container is known as hydrostatic paradox. In order to maintain the equilibrium, sigma Fi equal to 0. That means we have to consider all the vertical forces that is acting on the system. So for this container, here weight of the liquid that is acting downward, whereas pressure force that is acting upward. So here Ps represents the force exerted by the container wall against the pressure exerted by the liquid, and W indicates the weight of the liquid, and Pv, that is a vertical component of Ps. So for equilibrium, there should be an additional force that is acting downward as P into A, that is greater than W. As could be seen from this figure, there is a force that is acting in an inclined direction perpendicular to the side. So the component of the force in the vertical direction balances the difference in pressure force and weight of the liquid. So sigma Fi equal to 0, so that can be written as P into A, that is the total pressure force that is acting at the bottom, equal to the summation of these vertical forces plus W. But for the third container, weight is more than the total pressure force that is acting. Same principle we can apply here. The vertical component of the force Ps, that is in upward direction, so that can be added to the pressure force so that it is balanced with the weight of the liquid in the container. So the apparent contradiction in the hydrostatic force on the container base and weight of the liquid inside the container is known as hydrostatic paradox. So component of this force in the vertical direction balances the difference in pressure force and weight of the liquid. Let's work out a problem. That is, in this problem, pressure is given, but we have to express the pressure in terms of head of water and mercury. So expression is P equal to rho GH, or here I have written as P equal to S into rho G into H, where S means specific gravity of the corresponding liquid. S into rho G means it indicates the specific weight of the corresponding liquid. So here we are interested to find out the head of water and mercury. So head equal to H equal to P divided by S into rho G. Here specific gravity of water equal to 1, whereas mercury it is equal to 30.6, and rho G, that means specific weight of water, that's equal to 9.81 into kilonewton per meter cube. So specific gravity of any liquid multiplied with the specific weight of water will give you the specific weight of the corresponding liquid. So you can very well calculate the pressure head in terms of water and mercury. Now we have to calculate the absolute pressure. So we have learned previously that absolute pressure equal to atmospheric pressure plus gauge pressure. So atmospheric pressure is given to you and gauge pressure is available, so you can calculate P absolute. Now we comes to the end of the session. So we can continue fluid statics in the subsequent videos. For the time being, it is enough. Thank you.